principles of USBL. This is what we're going to cover. We're going to go to refresh what we did in the webinar last week. So those that weren't on the webinar on the overall principles one, we're going to sort of touch on what we did last week just to sort of get everyone back to the same standard. And then we're going to look at what it's being used for offshore. Why is USBL being used? And then we're going to look at the principles of it, all the measurements it takes, and the tracking methods, the tracking operations it takes. And then finally, we're going to touch a little bit on the calibration of the system called Cassius. All right, not too detailed on that one, but just enough to get an understanding of what we need to do and why. So, overview first of all, what is USBL? For those that are on last week's webinar, or those that have seen it before, this should be fairly straightforward. So type up on the screen or on the chat what you think USBL stands for. Let me know. Ultra short baseline, straight in, Rashida. Gold star there. Anybody else? Type it in. Ultra short baseline. Absolutely right. Yes. All good. It stands for ultra short baseline. The reason being is that, remember, we have a fixed transceiver mounted to the vessel, and we have, thanks Martin, we have these references that we're measuring everything by are installed in the transceiver. So these are hydrophones around our transmit element in the middle, and these are only a few centimeters apart, in fact, about 3 centimeters apart. So the kind of, in summary, really, of what a USBL system is, it is a acoustic positioning system used for underwater, obviously. It measures range, bearing, and elevation to a target. All right, so it measures a three-dimensional point in space of the thing we're trying to track, and it uses a multi-element transceiver, all right, which is known as or we call it HPT. So have a guess. What do you think HPT stands for? Type up on the screen or on the chat. What does HPT, do you believe, stand for? I just understanding so people want to know what it stands for, because I was working for Sonardyne. I've been working for Sonardyne for 6 years. It took me 6 months before someone told me what it stood for. Everyone just high performance transceiver, high power transceiver. Lots of different answers coming in. Everyone, it's the P in the middle that's the challenge, isn't it? It's the bit. What does the P stand for? High power, high performance. We have 2 answers already. In actual fact, the real answer is performance. So HPT stands for high performance transceiver. Sometimes we have people saying high precision transformer is the other thing, but it stands for high performance transceiver. All right. So the other thing we talked about in the webinar last week is that the precision of our USBL system. So we use it for tracking objects underwater, ROVs, subsea beacons, lots of things. We'll talk about all the things it's used for later. But the precision of a USBL system is dependent upon water depth. And as we covered last week, and I'll just refresh it again now, the reason for that is that the further you are away from the thing you're tracking, the less precise you're going to be. And the analogy I use for that is if I was to draw a target on a blackboard or a whiteboard and gave you a red pen and put the red pen in your hand and said, dab the bullseye as many times as you can in 30 seconds, I would expect you to see a really tight set of grouping, like you can see on the screen there. Then if I gave you a green pen with the same size target, but I put the green pen on the end of a snooker cue or a pool cue and got you to repeat the process, dab the bullseye as many times as you can in 30 seconds using the pen on the end of the pool cue, I would expect to see grouping that is slightly more spread out, because your precision of those dabs is going to be slightly less because you're further away from the thing you're from your target, if you like. So the longer this line is, the further your device or the object you're tracking is from the vessel, pardon me, then the error, the more area you're going to have for its position subsea. That's just basically a fact of life. All right. So as you can see on the screen there, we can use it for tracking all sorts of things underwater. And here's some pictorial examples of those. So we clearly ROVs, so remote operated vehicles, subsea robots, if you like, can be, we need to know where they are at all times. So they'll be tracked using our USBL system, given a position underwater, tracked from the surface. Towfish, for sub-bottom profilers or side scan sonars and SAS sonars, etc. Lots of applications for those things. Towed behind the ship, clearly they need to know where they are as well. If we're taking survey data, we need to have good position data applied to that as well. And USBL fixes what we use to get those. AUVs, untethered vehicles in any sort of shape and design, we'll track those using a USBL system mainly, and I'll give more information on that later. Smaller ROVs, so for shallow water operations, for monitoring the holes or doing some work on the seabed, and obviously divers as well. If divers are down, it's often quite good to know where the divers actually are, and if in the case of an emergency, knowing where the diver is or was is quite important, and having a USBL system enables that very easily. Another application for USBL would be in dynamic positioning. This is what we call LUSBL, we talked about last week, which is a combination of sort of putting of a long baseline array on the seabed and then a USBL system on the rig on the surface. Could be a rig or an FPSO or drill vessel. And that will be dynamically positioned by using the seabed references on the seabed as a reference to give position on the surface for the vehicle, for the vessel. And that's another sort of application of USBL in that regard, where we call it LUSBL. So the products that deliver that in the Ranger the Sonardyne family are the Ranger 2 family. So actually, again, I've just noticed that we've got the number 2 missing off 2 of those. So just making a note of that for later. The Micro Ranger 2, Mini Ranger 2, and Ranger 2. So of these families, the Ranger 2 is your full kind of offshore, deep water, larger vessel. Mini Ranger 2 is more kind of shallower water or for smaller vessels. But shallow water, we call 1,000 meters shallow water. So anything down to 1,000 meters, but there is an extended range version of 4,000 meters. And then we've got the Micro Ranger 2 for really, really sort of in water, sort of coastal water, shallow water stuff, but also used in some autonomous applications as well. The sorts of vessels these might be on, so Mini Ranger, Micro Ranger rather, be on sort of something like a small rib or a small boat, inshore craft. The Mini Ranger is for sort of medium range size vessels, and this is a reasonably large medium range vessel, but it could be a sort of standard survey catamaran. And then your large offshore vessels for Ranger 2. And really the sort of the crossover point between these is the cable length. Mini Ranger 2 has an Ethernet connection between the transceiver and the computer on the vessel, so you're limited by the length of cable on that. So if you go for a much larger vessel, then it's the Ranger 2 stuff that they're going to use. And generally they have different applications. The software itself is pretty much the same. But the LUSBL, or the DP side of things, is similar software. It's the same package of software, but some extra features that give it the certification to be used for dynamic positioning for these larger vessels. And that product is called Marksman. So similar in design, a few extra features that make it sort of certified for that purpose is called Marksman, LUSBL. Another application for USBL is something called iUSBL, right? Have a guess. What does I stand for in iUSBL? Before I show you what it does, see if anyone's heard of it before. It'd be interesting to see. So inverted, says Satish. Well done. Anybody else have a guess? Inertial. These are all good guesses. Inverted or inertial. Inverted, says Anthony. Good stuff. Inertial. Oh, we've got a 50-50 split now. I wonder who's going to be right. Actually, those that said inverted, that's the one. So what we do is, instead of tracking the vehicle reference to the vessel, we put the transceiver on the vehicle, we put the transponder on the vessel, and we basically flip the whole thing upside down. So it's an inverted USBL. The reason for that, if the long layback tracking, if we're towing something behind the vessel, it's a long way away, so the signals coming back are very quiet, and we're trying to hear them at this end over the thruster noise, etc. as well. So it makes it more efficient if we put the transceiver element, the USBL head, on the vehicle with a long cable going back to the vessel and a transponder on the vessel. and then we basically interrogate in the inverted stage. So we're still getting a position on here for the vehicle, for the vessel, reference to the vehicle, and using GPS we can actually apply that in reverse. But it's basically another version of USBL, but in upside down form. Hopefully that makes sense. And the software itself, whichever package you got, whether it's micro ranger, mini ranger, or the full ranger too, the software is identical. It looks the same. However, the different packages, different variants have slightly different features. So there'll be sort of certain features that are enabled or disabled depending on the package you got and the requirements for your operations. And it also meets the price point of whatever you want to, how much you need to pay for your system. There's no point paying full whack for a system you don't need all the features for, when you can buy a lower cost option that gives you the features you need to use for your particular operations. But this is the software. It's pretty much the same. Not very intuitive. Nice chart display. Shows your vessel. Shows the thing you're tracking. You can switch them on and off down here to start and stop tracking. Status for all your hardware and the position data, etc. up there. Lots of other tools involved in it. If you want to know more about that, you can look on our YouTube channel. There's lots of information about Ranger 2, and also you can always come on one of our training courses and find out exactly how to use it. In terms of the hardware, then we're just going to look at now on in order to before we carry on though, let's just make sure, is everyone happy so far with the kind of overview of USBL, of what it is and what it's being used for? Again, if you're happy, give us a thumbs up or a tick on the participant window, or if you can't use those tools, just say, give us a yes in the chat box. Good stuff. Yeah, everyone's saying yes. Let's look at what we need then. In order to derive a position for something underwater, what hardware do we need on the system? There's two things we need to make. So it's an acoustic system. So what's the thing that's making the sound in the first place? Up on the chat or in the on the screen. What do we need mounted to the vessel to just as part of the USBL system? It sounds obvious, but just to make sure you're still listening. That transducer, yes. And what do we need subsea? Transceivers, says Martin. Yeah. And what do we need on the object that we're tracking? A transponder. Yeah, a beacon. Yeah, all these are good words. All right, so on the vessel, we need our transceiver head, the sonar head itself. All right, as we said already, the HPT, high performance transceiver. That gets mounted on the vessel, and that is what's creating the noise and also listening for those responses and measuring where the object is. And as you said already, we need a beacon or a transponder on the object that we're tracking. All right, lots of different types of transponders. I'll give you a guidance through those first of all in a second. But first of all, and obviously in the middle of there's going to be a computer and some other stuff as well required, which we'll talk about a bit later on. But just looking at the acoustic side of things, these two are the key parts of a USBL system. The bit that's making the sound, the bit that's responding, and then basically being measured at the top again. So the transceiver itself, all right, so this is an HPT 5000, which is a transmit element in the middle. This is making the sending out the acoustic signals, and they're all wideband digital acoustic signals these days, so everything's digital and codified in sound waves. And then we have these hydrophones receive elements around the outside that are listening for the response back from the transponder. All right, we'll talk about how that works a bit later on. There are a few different types of transceivers you've already seen on a picture. So the HPT 5000 has 5 receive elements. There is the 7000 with 7 elements. There's the 13000 with 13 elements. And then Mini Ranger 2 is called the HPT 3000. So how many elements does that have? Everyone's saying 3. Let's see if you're right, 4. Actually, you're all wrong. It's 5 elements. It's a trick question. We just ran out of numbers. So the 5000 does have 5, the 7 has 7, the 13 has 13, and the 3000 has 5. It's a similar design. The transducer face is similar in design to the HPT 5000. It's just been tailored to be fitted on a smaller vessel and is tuned for better for high elevation tracking as well. So it's pretty much 90 degrees tracking. The HBT 5000 has similar beam width as well, actually, but this actually is slightly better at filtering out the noise above, and it has a few extra toys inside it as well, just to make it more suitable for smaller vessels. And then we have the Micro Ranger 2 system, which has a slightly different design of transceiver, which is called the MRT, or we like to nickname it here in the UK as Mr. T. And anyone that's familiar with the US show, the 18, will know who this chap is. He's called Mr. T, which may not be suitable for most of you guys around the world if you don't know this cultural reference, but for us in the UK, trust me, that's hilarious. Right? Now, you need to have your transceiver fitted onto some sort of pole in order to get it in the water. The transceiver needs to be in the water below the keel, all right, and as far away from thruster noise, etc. So positioning of the transceiver is quite important, but having it down, obviously in the water, but below the keel to give you good line of sight to everything you're tracking in all directions, all right? So you need it on a pole of some sort to do that. So the solutions, the options for that is through hole solutions. On the right hand side there, you can see this is a deployment machine. It's basically an inverted periscope. There's a hydraulic ram that pushes the transceiver out through the bottom of the vessel through a gate valve here as well, right? And this is basically the sea chest inside one of those with a gyro USBL fitted to it. I'll talk a bit more about that later. The gate valve underneath is currently closed, obviously, to stop the, and the sea chest is open so you can see inside it. But then obviously this would be sealed up on the outside. The gate valve would open, and you can drive this down through the hull. And also, just for your information, now the latest version of Ranger 2R software, you can actually control our version, because we do also make deployment machines, and the control system for the deployment machines, it can be embedded and be operated from your Ranger 2 system nice and easily. This is another through-hole design, which is basically craned in position. So it's a longer pole. You can see here we've got some hydraulic clamps that seal it off on the deck. So this would be something on a rig or a larger vessel. So it'd be sort of deployed on a pole and then kept there. And generally, this is more of a dynamic positioning type vessel. That doesn't really sort of move through the water very much. Obviously, the benefits of this system is if you needed to move the vessel, you can retract it quickly and then move away without potentially damaging the pole or the transceiver. That's all good. That's your through-hole stuff. The other option, obviously, is over the side. And then here you've got the two extremes of cost for different systems. On the right-hand side here, this is another hydraulic system. It's welded to the side of a ship. Much easier to install than putting it through the hull, as you can probably imagine. It's not a dry dock job. You can do this alongside. You can weld this to the side of a ship. You've got a clamp at the top and a similar clamp 90 degrees down the side of the ship. This would basically hinge into position and lock in place, and then give you that transceiver below the keel quite nicely. And then at the other end of the scale, you've got Micro Ranger 2. This can literally be mounted on the end of an aluminium scaffold pole. All right, so this is literally a wall plate and a scaffold pole with a special plate that that comes with the system. You can bolt it to a pole, so you can put it over the side of a rib or a small vessel, dead easy. All right, so over the side solutions, obviously far quicker, not quite as rigid or as secure as maybe as a through-hole system, and not as easy to deploy, but they're all good options. So let's look at the beacons themselves. There are a whole array. This is not an exhaustive list, all right? There are lots of different types of beacons that Ranger 2 can track. Currently, it's all 6th generation stuff, so our 6G hardware. So this will be a compact 6 for LBL operations. When they're being deployed, you can usually get a position for them using our USBL system. So they'll be put on the seabed and given a position from a USBL. And then we've got smaller beacons for like WMT, which is a wideband mini transponder. And then this one over here is the WSM6 Plus, which is a wideband sub-mini transponder. These have very similar capabilities. They've just got different battery life lengths and different power options and slightly more functionality in this one for sort of more complicated scenarios. But this is an all-rounder. The WSM6 Plus is a brilliant little beacon. It's light, short, it's reasonable power. Good length of battery, good depth of ratings, really useful and versatile little beacon. This one in the middle is release transponder, which can be tracked as a beacon. You can put a load on the bottom, and when you want to place the load on the seabed, you simply send a release command from Ranger 2, into this beacon, and it will deposit the load on the seabed, and you get a position for it as well because you're tracking it like a beacon. And then right at the end here, nano, there are lots, I said there's lots of other beacons, and basically pretty much any of our 6th generation transponders of any design can be tracked and positioned using Ranger 2, including SSTs, Fetch, Pies, you name it, they can all be put in position. But the Nano as well was probably the cutest thing that we make. That's the size of it. That's in my hand in Plymouth there. It's a picture that I took a little while ago. So you can see the scale of it, and I haven't got very big hands. So this is less than the size of a can of Coke. It weighs about 200 grams in water. The cutest thing that we make. Ideal for tracking divers or small ROVs, if you saw in the earlier picture. Everyone happy with that so far? That's the kind of overview and applications and some of the hardware we're looking at. Again, give us a thumbs up or a tick if you're generally happy with that. Good stuff. People still engaging. All right, moving on. Let's look at how we get a position. People are dropping in and out. We lost their connection. So if we want to get a position for something subsea, there's 3 bits of information we need to know about it. All right. So if you want to derive or calculate a 3-dimensional point in space for something underneath you, what 3 bits of information do you think you need to have? What is our system measuring? In the chat or on the screen? Three things I need to know. Time traveled, yeah. But what's that time travel going to give us, Rashidi? Or anybody else? Distance, range, yeah, we need to know how far apart it is from how far away it is from the vessel. Micro Ranger 2 is about, again, it's a slant range of about 995 meters for that. So you can have someone down to 1,000 meters if it's directly below you. But basically, it's a slant range limited to 995 for Micro Ranger 2. But yeah, you're right. It's range, bearing, etc. So yes, all good answers. X and Y, depth. Yeah, that's another key part of it. Range, angle, and SOS. Yeah. Speed of sound. Yeah, good. So what we're looking for is range from the vessel, how far away it is, the bearing from the vessel relative to our ship's head, so we know which direction it is, and then obviously the 3-dimensional point of space, we need to know its elevation angle or the depth, as someone's already said. All right, so these are the 3 things that our system is measuring to derive a position for a transponder. Starting then with slant range, the range, how far away it is. This is a simple kind of time measurement, really. So someone mentioned time earlier on, Ashidi, I believe. So with and this is what we do is we send an interrogation into the water from our transceiver, and the transponder or the beacon will respond with its own response. And then what we do is, or the system measures how long that process took. So if we send an interrogation, it measures how long it takes before we hear the response back at the vessel end. So we know that speed equals distance over time, and therefore distance equals speed multiplied by time. In this process, if we send an interrogation and we get a response back 2 seconds later, how far apart are those 2 objects? How far away is the beacon? With the sound's velocity in this example of 1,500 meters per second. So the speed, that sound is traveling at 1,500 meters per second. We send an interrogation, we hear the response back 2 seconds later. How far apart are they? So Sean's saying 3,000, Rashidi's saying 1,500, Mahmood is saying 3,000. We have a split decision again. We have a split between 1,500 and 3,000. Who do we think is right? Let's find out. Right, those that said 3,000, Sean's changed his answer to 3,000 to 1,500. It's 1,500 because it's a 2-way travel time. This acoustic signal has gone there, and another signal has come back again. So the total travel time is 2 seconds. So although the acoustics have traveled 3,000 meters, that means this is half that distance away. Yeah, hopefully that makes sense. So what happens is we're basically half the time it takes. It's the 2-way travel time. Half of that gives us the range. Now, in reality, does this happen instantaneously? If I send an interrogation to that beacon, will this beacon respond instantaneously? Yes or no? No. Yes. Oh, we haven't a split decision. The answer, it is actually a no. It can't instantaneously respond because it has to detect this and it has to process a response. Those that are on last week's webinar will know that the response that we send back includes some diagnostic telemetry data as well. So some signal strength and some forward error correction code and all the sort of stuff that your mobile phone is doing in the background is sending back kind of health check data all the time. So every time it sends a response back, an 8 millisecond pulse back that basically says, here I am, it also embeds loads of data into it. So it needs time to generate that and process it. And so that basically gives us a bit of a delay at this end. Now, any delay at this end will be added to that travel time and therefore put our range slightly in error. Now, there are a number of ways to mitigate that, and some people have already said in the response as well. You could timestamp the signals. You could basically you could calculate how long that delay was and put that into that data so that the system could counteract it. All that sort of stuff. Lots of really Gucci things to do. But what we do is something far simpler and actually more useful for us. Is we basically give it a turnaround time. We tell it how long to wait before it sends a response back. So it detects a signal, starts its own little internal clock. As soon as the turnaround, whatever the turnaround time is set to, and I've just put an example here of 200 milliseconds, and it basically, as soon as that time has elapsed, it then sends back the response straight back to the transceiver. So then at the ship end, or the vessel end, that total travel time is now 2.2 seconds in this example. So the first thing the system does is remove that turnaround time because it knows the delay, because both ends are programmed to be on the same delay. So it knows that there's a 200 millisecond delay on that particular beacon, takes it off, and therefore calculates the exact acoustic distance between the two, which is 1,500 meters as before. In summary then, for the slant range equation, everything is based on this equation for slant range, all right? So two-way travel time minus that turnaround time delay multiplied by the speed of sound, all divided by 2 to give us the slant range. Does that make sense? If that makes sense, please please put a thumbs up on the thing. Verizon, you've got a question, you've got a hand up. Is that a question? If it is, type it in the chat. And if I can't answer it, Stu will cover it for me. If it's not a question, then just give us a thumbs up. Now, the key part of this equation, really, is that speed of sound element at the end. Obviously, we want to reduce the number of error in our system. So if we've got a good, accurate speed of sound, then our range equation is going to be correct. So there's a few ways to get speed of sound into any acoustic system. You can monitor directly, so you can have any of our subsea equipment that can be fitted with a sound speed sensor, direct sound speed sensors such as this, and you can feed that into the system, either with a cabled or acoustic, it matters not, all right? The other thing you can do is do a profile. So if you take a profile through the water column, you can get this various sound speeds at different depths. You can program that into the system, and the software, the algorithms can help compensate for the various and give an average through the water column, etc., and compensate for any sort of problems. And that can all be entered into the software relatively simply on the environmental settings. So you can have your fixed references coming in here if you can read them off something else, or you can basically have a sound speed sensor plumbed into the system, or you can use a sound speed profile and load it here. But if you haven't got any of that hardware, that's not a major issue. If you're on one of these sort of the lower cost options like Mini or Micro Ranger 2 and may not have some of that scientific equipment, that's fine. There's an estimated profile you can enter. As long as you've got a GPS feed into your system or GNSS feed, it'll tell you your location in the system. The system knows where it is in the world. There's a World Ocean Atlas as part of the software install, and it will basically take a profile, a historical profile, but roughly for that sort of time of year in that location, as near as it can, to give you a kind of a pretty good sound speed profile roughly for that area. So it's a good start of attempt. It's not ideal, but it's better than nothing at all, better than having just the defaults in the system, if that makes sense. So that's the range calculation. Let's go on to then the bearing. This should be fairly straightforward, all right? So what we have is our transceiver. As you said already, we had a number of hydrophones installed on the USBL head, and this is the forward mark, or the ship's head, or the bow, all right? And the beacon we're tracking is somewhere over here, so the waveform is wavefront for the response is coming from this direction. So we know where the elements are, when they're precisely manufactured. And as a sound wave travels across the face of the transceiver, we can measure the time of arrival of that signal at each of the elements. Blink and you miss it. So again, I'll just run that again. As it's coming across the sounds, we can see that different elements are activated at different times. So by measuring the time of arrival, it gives us the difference in time is basically proportional to the angle of approach. That should be fairly straightforward. Is everyone happy with that in terms of the range and the bearing elevation, bearing measurement? Good stuff. The next thing we're going to talk about now is the elevation angle. This gets slightly more complicated. Bear with me, I'll make it as simple as I can. So a signal coming straight up from underneath will activate all of those receive elements at pretty much the same time. But what we look at the phase of the signal. We can see that all these are on the same part of the signal phase, or the waveform as it comes through. But when you look at one that's coming from an angle, it will activate those at different times, but also at different points in the signal phase as well. So again, if we analyze that, we can see that if we look at the phase of the signal, this one, that one, that one, they're all at different parts of the sine wave cycle, if that makes sense. So by looking at the phase difference between the various signals, we can determine the angle of approach into the transceiver head. This is simplifying it drastically in reality, because we don't use sine wave signals, they're digital signals. So the phase calculations are a lot more complicated, but in principle, in simplistic terms, that's what the system is doing. And another analogy for this is like waves on a beach. If you're stood on a beach, you can see the waves approaching straight towards you, like you see on the image there. It's pretty easy to see which direction they're coming from. You can know they're all basically hitting the beach all at the same time. When the wind's in a different direction, you'll see the waves hitting the beach at a different direction. They'll ripple down the beach as they come. That's effectively what the transceiver is doing with the sound waves as they pass across the transceiver base to determine the elevation angle at the same time as determine the bearing angle, the heading angle from it as well. Does that make sense? Thumbs up or ticks, ticks or thumbs up. Good stuff. Thank you very much. Because now we understand how we measure the various parts, we're going to look at what it does to track various things, the different modes of operation for tracking an object. Starting with the relatively simple version of responder operation. This is ROV tracking or any other tethered vehicle, could be a towfish, for example, right? So if you've got a tether and a cable, a comms cable connected to your ROV, you have your transceiver or transponder on the ROV plumbed into that cable. So the cable will be out of the PC into the multiplexer, down through the fiber optic cable to your vehicle, into a demultiplexer at that end, and then into basically straight into your beacon. So what happens here is we send the interrogation down the cable rather than acoustically. There's still a sort of version of a turnaround time, but we call it a transmit wait. So it's the same sort of thing. It's a processing delay that's known by the system. After that delay, it then sends an acoustic response back through the water for the transceiver to measure where it is in the water. All right, so interrogation down the cable, acoustic response through the water. That should be fairly straightforward. STB, well, you'll see this hopefully in a minute as well. We'll answer that question later in the presentation, hopefully. All right. The next thing we'll look at is transponder operation. So this is two-way acoustics. Now, it doesn't matter what you're tracking, whether it's a beacon or diver, your basically transponder will be in the water, and this is now the single interrogate or individual interrogate. All right, so we'll send an individual interrogation to the object we want to track, and it responds back. And so now we're tracking everything individually, one by one, in this mode, in transponder mode. Okay. Now the communications that are happening is an individual interrogation signal, or IIS. All right, goes into the water, and that IIS is basically using the beacon's address. All the beacons will have a 4-figure number for their address. All right, the first 2 numbers are their family group, so you could have all your beacons set to 21 something, and then you'll have up to 14 beacons that in different channel numbers. So 2101. 2102, 2103, etc. All right, so they all have their own individual phone number, if that makes sense. So the individual interrogation is specific to one beacon. So that means that's the only one that will respond. And that will respond with what we call a common response signal. So it's basically saying, 2101, where are you? Common response would be, here I am, because it's the only one that's going to respond, all right? So it doesn't need to tell you its address. So that's basically what goes on. So individual interrogation, common response, individual interrogation, common response, all right? So that's tracking things individually or single interrogate. So effectively, your single interrogate or individual interrogate is like a point-to-point communications. Wherever you interrogate, that's the only thing that's going to ask, a bit like a phone call. All right, so when you ring one number, one person answers, and that's it. Now, the next thing we're going to look at is common interrogate. All right, this is where all of our subsea beacons are programmed to listen out for a common interrogation channel. All right, it's basically like a broadcast channel. So saying everyone on this channel respond when you hear this interrogation. So we'll send out the interrogation into the water, and they will all respond individually. All right, so what we have in terms of communications here is a common interrogation that goes into the water, and then an individual reply coming back. They all wait their turnaround times, and then they respond after their turnaround time. And this is why that turnaround time is quite important, because we can program on the fly, even whilst underwater, we can tell these beacons what their turnaround time should be. They're programmed before they go in the water, but we can change it on the fly. So if we realize that these two signals are arriving back at the transceiver at the same time, the system is likely to miss one of them. Because if you've got like 8 beacons down there you're trying to track in common mode, it is achievable as long as we have 8 different responses coming back at different times at the transceiver. Now the software gives you a warning if that's getting close, and it's dead easy to change. It's a couple of mouse clicks. But basically you change the turnaround time so that you're getting different responses back at different times. It's like trying to catch a bucket full of tennis balls. If I threw a bucket full of tennis balls at you, you'd probably catch one if you're lucky, all right? But if I took the balls out one at a time, you'd catch them all. So this is what we're trying to do here, is manage our tennis balls, if you like. So CIS and IRS are common interrogate and an individual reply. So common interrogate would go out on a group channel, and their individual responses would all contain their addresses, so we know which one's replying. So it's like a group chat. So it's not point-to-point comms now. It's basically a group chat, a bit like a WhatsApp group. All right. Within a WhatsApp group, you send a message to the group. Only the people in the group will respond because they're the ones that hear it, and you can tell by seeing who's replied who it is that has replied. So you can identify the person who's replied. So that's what we're doing here, is like a subsea acoustic WhatsApp group. Now, with acoustic travel here, right, the update rate, so people often ask what's the maximum update rate we can get from USBL? Well, historically, and with some of the other systems out there, you think that the update rate will be limited by the acoustic travel time. So as you said in the earlier example, if this was 1,500 meters away, you've got a 2-second sort of two-way travel time for the acoustics, roughly, all right? So that would probably limit the update rate to 2 seconds for that range. And if it's further away, that would be slower again, all right? But what we do is something a bit clever than that. We use something called ping stacking. So the system, you can dial in whatever update rate you want out of the system, and the system will automatically apply ping stacking, which is sending interrogations before we heard the previous response. So once we've got a good fix on that, it starts to basically juggle the interrogations by opening and closing range gates in the transceiver to look out for those responses at the right time. So, and this can be done for multiple targets. It's automatically applied in both IIS and CIS modes in order to give you as close to what it physically can the update rate that you want. Now that could be in a full range of 2 system as fast as 1 second, regardless of the range. It could be 8,000 meters away, and you can still maintain a 1 second update rate, give or take a little bit. All right, there could maybe some overlap there, maybe adjust it slightly, but it will get to it as close as it possibly can. Now, the other sort of tracking method we're going to look at very quickly is AUV operations. Now, when you're tracking an untethered vehicle like an AUV, these are generally navigating themselves or guiding themselves around using an inertial system, which do drift over time, which you'll find out in a couple of weeks' time as you go through our inertial webinar. So in order to fix that drift, an AUV needs a regular update of its position. Some of these AUVs will surface and get a GPS fix and then dive again, but that takes up precious energy. If you can keep your AUV submerged, then better. Now, Ranger 2 robotics pack enables that, and what we have is another type of beacon, an AV track. It's a transceiver that then is installed on the AUV and is wired into your guidance computer on the AUV. And what happens when we're tracking an AUV in telemetry tracking or robotics mode is the interrogation we send to the AUV contains a time-stamped position data from the previous calculation. So if the previous interrogation, we would have got a position fix for the AUV. So that information and the time that we got it is included in the next interrogation to the beacon. This enables the AUV to go, well, I think I'm here now, but if I was there 2 minutes ago, then that makes sense. Then I'm on track and that's all working. All right. So that's basically a key part of what our robotics pack does. The other things the robotics pack enables, and it's basically a common response back again. So you get the response back in the normal mode. We get a fix for the position on this interrogation, and then that position fix is sent down on the next interrogation to the AUV. The other thing we can enable to do is kind of something called SMS, which is Sonardyne messaging system. So there may be a need for the AUV to either talk to a third-party system on your vessel, so basically we can send messages through our USBL system to the AUV and back again, all right, by using our USBL system effectively as a modem now. So in between or during the tracking phase, we can be getting free text messages, and they could be in any format, just converts into acoustics and sends it down to the AUV, and the AvTrack will route it to where it needs to go in the AUV. Relatively simple to set up, and it's a couple of clicks of the mouse again when you get the robotics pack as part of Ranger 2. The other thing that an SMS enables to do is if your AUV has a message to send to the third party at any time, it could be a health message or a sort of a tripwire of something like when its battery is 25%, it can send it back at any time and it will get patched through automatically as part of the modem settings in Ranger 2. And the same is true for swarm AUVs, for multiple AUVs. So we can position fix all of these, send all that position data down to the AUV, and it will relay it to all of the others. Or we can position other ones relative to this by using baseline functions. We can monitor health checks, and basically it can do lots of stuff. If you want more information on AUV and robotics pack, look on YouTube. There's loads of good stuff about it. All right. So that's the kind of main tracking methods. But one thing I need to touch on is layback tracking. So things are layback or a long distance, either sort of laterally from the vessel. The most direct sort of the range between the two, the direct path there, is not always what we measure. Now, you're probably aware that the water has different temperature layers down through down through its depth, and each one of those affects the sound speed. That's why we talked about the sound speed profile earlier on. Now that has the effect of bending the sound wave, so we end up with this refracted path that comes back up to the vessel, which means that the apparent arrival angle at the transceiver is sort of artificially elevated, if you like. So it looks like the thing we're tracking is at the wrong depth, and more importantly, the wrong position, because this is kind of an arc that comes between the two. And that position error is relatively simple to overcome in our systems, because most of our beacons have fitted within them a depth measurement. All right. So if you're going to be tracking anything laterally, make sure we have a beacon that's fitted with a depth gauge. So during tracking, we can basically switch on, whilst it's subsea, we can switch on depth aiding, and it sends a message down to the beacon to say, we're now doing depth aiding. So every time it gets, it measures its own measurement, it measures its own depth, records that, and sends it back as part of its response. So effectively what we have is this beacon with an XY area, not sure where it is. We're measuring the slant range using acoustics, and we're measuring the depth using the depth sensor. So therefore we can calculate the lateral offset to get its position. Remember the angle is taken out here, the bearing angle is taken out here. So now we can know exactly where that is, and we can basically correct for that X and Y error. Which, this is our hypotenuse, and this is side A, and this is side B. Good old high school Pythagoras coming into play in a modern USBL system. Those Greeks knew a thing or two. There is a time and a place to use depth aiding and not to use depth aiding. Basically, if you imagine a straight line straight down to the seabed from your transceiver, 30 degrees either side of that is the place to not use depth aiding. So depth aiding is only used outside of that sort of 60-degree cone, or plus or minus 30 degrees. And the reason for that is depth sensors are not the most accurate things in the world. There's usually an error bus between the depth sensor and the acoustic range that we're measuring, a highly precise acoustic range. So if you've got depth aiding applied within that kind of key cone underneath the vessel, then what the system does is try to find a position that both of those measurements match. So over time, your beacon will track in a sort of circle like that. And that's a clear indication that depth aiding is applied inappropriately. Simple, just turn it off in the beacons table. And if you're around the 30-degree mark and you see it sort of moving around a little bit, then try it with and try it without and see which one gets better. But generally, outside here, depth aiding is used. Inside here, depth aiding isn't, for this very reason. Now, that's the tracking methods and operations. Is everyone happy with that? Again, thumbs up and ticks. Good stuff. The last thing I'm going to go through just very quickly is just thinking about the calibration thing. And this is where someone mentioned earlier on about an MRU, STBE. I don't know what your first name is. So we've already said we have the transceiver fitted to the vessel, right? And currently what we talked about with getting those positions is kind of relative to the vessel. But if we want to get an absolute position, or these things are northings or lat and long for the thing we're tracking subsea, what else do we need to fit to the vessel? Ah, thanks, Steph. What else do we want to have on fit to the vessel then? If we want to get an absolute position, a lat and long or an eastings and northings for our beacons. GNSS, yes, GPS. So we need a GPS system or GNSS system fitted to the vessel in order to give a global reference for a world reference for our vessel. And as some of you already said, the vessel is moving all the time, right? So we need to have an MRU, a motion reference unit, or a heading reference unit or something installed into the vessel to tell our system that the thing it's attached to is moving. Because if we don't tell it it's moving, then it just believes to be the target underneath it is the thing that's moving. Now, all those things are installed on a vessel relative to a common reference point. This is certainly true for larger vessels. Smaller vessels, not so much, all right? So yes, a gyro is an MRU, is also a gyro. So at the moment, the transceiver, before we got to calibrate it in, it's just in transceiver frame. It just knows where it is in relation to itself. But we need to put it into the vessel frame, so put it where it's in relation to all these other bits and pieces. So to do that, we install into the system all of the offset measurements for all these various bits of kit, either relative to the CRP or relative to the transceiver. It depends on the application and what you're doing. CRP is normally about water depth, about the sort of the water line of a vessel in the sense of rotation of the vessel normally. All right, so that's our kind of where everything is. We put all that stuff into the system, and these are physical measurements. And with the best will in the world, with the best dimensional control, there's going to be some small amounts of error in that. And small amounts of error at the surface can translate to larger errors on the seabed. Remember the snooker cue analogy. You make a small adjustment at one end, you can make a large adjustment at the green pen at the other end. All right. So in order to sort of calibrate all those in, we use something called the Cassius software, which is part of the Ranger 2 system, is the calibration of attitude sensors in a USBL system. That's what it stands for. So in order to achieve that, we place a beacon on the transponder on the seabed, and then we perform some maneuvers over the top of it. The first thing the Cassius does what's called a box-in, to actually give this a boxed-in global position on the seabed. So it's now a fixed reference we can calibrate the rest of our system from. And then depending on the type of vessel, depending on the size of the vessel, the thruster systems you got on, etc., we do a number of maneuvers over the top. And then that gives us a number of position fixes for that beacon on the surface, on the seabed. Now, all these errors we see and differences in position here for the different positions of the vessel are basically just show you that there are an error in the offsets on the top, because basically everything the angles are looking bad. So what the system does is it basically tries to basically converge all of those points onto a single point on the seabed, because that's what we know to be true. All right. by changing those offsets in the system, it calculates what the offset should be to converge all that data into one single point on the seabed. Then you apply those corrections to your system, and it gives you a report such as this. And we'll see here that it gives us a percentage of precision, a precision percentage of water depth. So in this example, for the 1 DMS figure, we can see here we've got a 0.13% water depth of precision, which means in 1,000 meters of water, this system on this day, after this calibration, will give us no more than a 1.3 meter error on the seabed. Now, there are a couple of other things that can make Cassius's a bit easier, having the MRU installed within the gyro, the transceiver head itself. And this is called a gyro USBL. So it basically have our MOU and the transceiver into a single unit. Basically means you don't really need to do much with Cassius, because all your motion data is installed within it. 2 versions. There's our newest version, brand new, and this is our the older version we've got, the previous version. All right, so see, it's a lot smaller these days. You can make it a lot smaller, and it's exactly the same technology in both of these. It's just now in a smaller can, make it a bit easier to handle. But what we can do, so that can arrive to do a Cassius, and that relatively simple. But we can do a Cassius in Plymouth as an optional pre-delivery option. So we basically calibrate it here in Plymouth, ship it out to you. You just literally bolt it to your vessel, put in the offsets, do a couple of verification checks, and then you're good to go. No need to do a full Cassius, which is kind of a few hours work. Smaller systems such as the Mini Ranger and Micro Ranger, these have their own internal sensors automatically as well. They're like a cheaper version of a gyro USBL. So in here, there's a smaller MRU, and there's an even smaller one in the Mr. T. And so technically no Cassius required, but the Mini Ranger 2 software does enable you to use external sensors if you wish. If you are using external sensors, then you do need to use do a Cassius. The Micro Ranger 2, the Cassius software is not part of that software. It's trimmed down, so there's no Cassius required for that. However, there are some optional alignment tests which take about 15 to 20 minutes, which we recommend if you want to improve your system performance, but pretty good going as it is. So that is 1 minute over. I've run over a little bit, but I did start with 1 minute late. So let's look at what we covered during this webinar. We gave a quick overview of the system. We looked at what USBL is and talked what we did in the first webinar and what it's used for. We looked at the applications, what it is being, what sort of things are we using to track USBL, from ROVs, divers, seabed beacons, AUVs, etc. Basically anything underwater. We looked at how it gets those measurements, how we get the range measurements, the bearing measurements, and the elevation measurements, and get to derive a position for that beacon or subsea. And then we looked at the tracking modes of operation, the responder mode, the individual transponder mode, the common transponder mode, and telemetry tracking and robotics for AUVs. And then we finished up with a very quick kind of overview of Cassius and why that's required. That completes the webinar. But if you want any more information about anything else that we do in terms of our training courses, go to our website. You can put in sonardyne.com and just search for training if you can't find it, and you'll see our training courses there. There's also links to our website on our LinkedIn page and on our Twitter page as well. By all means, go to those. I know many of you already follow us on LinkedIn, and we do appreciate. We really like having our followers watching what we're doing. And if you've got any questions at all or any more information, please feel free to email us. training@sonardyne.com. More than happy to chat to you at any time about anything you want. For now, though, thank you so much for joining us today. It's been really good having you all here. Thanks for participating, for giving us plenty of sort of feedback.